If you're familiar with the sphere that is math YouTube, then there's a pretty good chance you're familiar with the concept of a magic square, thanks in no small part to the infamous Parker square. The concept is simple if you're unfamiliar. Take a bunch of unique whole numbers and arrange them in a square so that the sums of each row, column, and diagonal are all the same, the magic sum. We as humans have known about these things for centuries, millennia even. The Magic Square Wikipedia page has a ridiculous amount of history. And you'd think that as long as these things have been known, we must have cracked their secrets ages ago. There have been methods to generate these squares that have popped up over time, but in the 2,000 years we've had documented knowledge of magic squares, the simplest one, the 3x3, didn't have a publicly known or published true formula until Edouard Lucas came along in the 1800s. And in this video, we're gonna walk through what took humanity 1,800 years to do, using only the tools at the disposal of a typical American high schooler. To standardize this, I'm going to be citing the US Common Core standards for math, just because of how widespread they are here in the United States. This video is not an endorsement of the Common Core curriculum or its adoption. I am in no way qualified to make any claims about education policy, but since these standards are here and pretty well known, I might as well use them. This video is also not meant to knock people who find the content in this video too difficult or confusing. The truth is, math education is hard. Just because the tools used are ones given to a lot of high schoolers doesn't mean that a high schooler would necessarily have the problem-solving skills to use these tools constructively outside of the contexts in which they were presented in class. This video is, however, a demonstration of how powerful the tools we have at our disposal can be, and showcase the problem-solving capabilities that the best-case scenario allows for. So, where do we start? Well, let's start by assigning some names for each of the 9 numbers in the square. Some letter, some symbol to represent each number when we start messing with equations. Because this video is obviously narrated, I'm going to be referring to each number as its own position of the square, but I understand that that can cause some confusion because of the symmetries in the square. For example, what I say is at the top left of the square could just as easily be in the top right or bottom left, just depending on how you rotate the square. A square rotated is still a square after all. But now that we have our numbers named, that's step 1 already done. This is when we get to start writing some equations. Each row, column, and diagonal all have the same sum, so that's a good place to start. This means that all of these are equal. But that's way too much for us to work with at once, so we need some way to narrow down what we want to work with, or at least start eliminating some of these variables. After a bit of trial and error, you realize that the center is involved in 4 of the 8 different sums, so that seems like a good quantity to focus on. If we can get some of these values in terms of any other value, the center is going to be the most useful. So, after fumbling around, you may find a relationship that one of the columns shares a sum with the diagonal that shares the same corner. And with some rearranging, you realize that you can cancel out the common corner on both sides of the equation, and you can solve for the center piece of the column. So now we have one of the sides in terms of the center and both of the bottom corners. Whether by deduction using symmetry or by trial and error, eventually you figure out that you can do the exact same thing with the opposite column. And just like before, we can simplify this. And now the square looks like this. And now that we have both of the edges in the middle row recontextualized, look what happens when we add them together. Both of the corner pieces referenced are added and then immediately subtracted, meaning that the sum across the row is just the center added 3 times, or 3c. But remember, this is a magic square. The sum across this row is equal to the sum across every other row, column, and diagonal. This means that our magic sum for any 3x3 magic square is just 3 times whatever the value at the center is. But what can we do with this information? The answer is hidden in plain sight, and to make it clearer, we're going to have to do some rearranging. Factoring a -1 out of one of these pairs of corners and adding some parentheses makes it a bit clearer. On one side of the center, we're adding some value, br minus bl, and on the other side, we're subtracting it. If we call this new term in parentheses x, it reveals the general structure of the lines that go through the center. With a bit of thought, you can convince yourself that this is the way it has to be. No 2 individual values in a magic square are the same, so we can say that this first value has to be some amount x greater than the center, or less if x is negative. But then if we have 2 of our 3 c's accounted for, this third value must account for the third c, while also complementing the change that was provided by the first x. And this is true for any line that goes through the center of our square. On one side of the center, we add some value, and on the other side, we subtract that same value from c to preserve the sum of 3c across. We are almost done. Let's check out these lines that don't include the center. Just like before, they have to add up to 3c, but instead of having convenient symmetry where we can just use one side of the center to complement the other, our middle pieces have to complement both corners at the same time. A couple quick equations can set this up nicely for both x and y. And with these steps, we've successfully taken 9 different numbers and used patterns to reduce the number of different values just to 3, a, b, and c. But we're still not quite done. Look what happens if I pick a, b, and c to be 1, 2, and 3. Sure, we do maintain the fact that all of the sums are the same at 3 times the center, but we neglected the other rules, namely, no 2 values in the square can be the same, and all values have to be whole numbers. All of the values have to be whole numbers, which means that anything subtracted from c has to be less than c itself, so that way there's still some positive left over. This means that a and b have to both be less than c, as well as their sum. At this point, it's probably a good idea to say that a and b should be positive. Having a negative number as a or b is equivalent to just having a positive value and flipping the square, so keeping these numbers positive means we only have to police adding and subtracting positive numbers, which is much more simple to keep straight. It should also be pretty obvious that a and b have to be different from each other, or else we'd have repeating values, so one has to be bigger than the other. The last restriction we have to make is about these edge pieces. What happens if once we take a minus b, we just get a again? That would mean we'd have another duplicate. So to avoid that, we have to say that the larger of the two isn't exactly twice of the other. And with that, we're done. This is the exact formula on the magic square page on Wikipedia, and it only took high school level tools alongside our own sense of logic and problem solving skills. When I sat down to derive this myself, I didn't know if it was possible to be successful with the tools I knew, and I was pleasantly surprised when I was able to finish. In this way, math is a lot like art. You can give just about anyone a paintbrush and show them how to use it. But it takes more than that to make a masterpiece. It takes a deep understanding and familiarity with your tools. It takes practice. That's where the math is, not in the brush, but in the artist. This video was made for the Summer of Math Exposition 2, hosted by 3Blue1Brown, and the goal was to make something both accessible, but also insightful and thought-provoking. Let me know in the comments if you liked it, or just with the like button, and I may be motivated to continue posting videos on this channel like this one. I have a few ideas for videos bouncing around in my head about STEM topics, so let me know if you'd like to see more. Thank you for watching.